name is Camron Chugg, and we are going to be talking about the photoelectric effect. In short, the photoelectric effect is when light strikes a certain material and it ejects electrons from that material. The phenomenon of the photoelectric effect was fundamentally significant in the development of modern physics because of the questions it raised about the nature of light, whether light behaved as a particle or a wave. These questions were finally resolved by Albert Einstein in the early 20th century. What is really important about the photoelectric effect is what Albert Einstein deduced from it. Einstein realized that there were several characteristics of the photoelectric effect that could be explained only if electromagnetic radiation is itself quantized. What seemed to be a continuous stream of energy, an electromagnetic wave, is actually composed of energy quanta called photons. In his explanation of the photoelectric effect, Einstein defined a quantized unit or quantum of electromagnetic energy, which we now call photon, with an energy proportional to the frequency of electromagnetic radiation. In equation form, the photon energy is E equals h times F, where E is the energy of a photon of frequency F, and h is Planck's constant. Einstein assumed that a photon would penetrate a material and transfer its energy to an electron. As the electron moved through the metal at high speed and finally emerged from the material, its kinetic energy would diminish by an amount E0, called the work function, which, in an equation that represents the energy required for the electron to escape the metal, which can be thought of like a threshold. So this E0 is also called the binding energy. So the work function is the binding energy. If a photon comes in with an insufficient amount of energy to this plate, or in other words, an amount of energy less than E0, or the necessary binding energy, then the electron from this plate will not be released from the surface, regardless of the intensity. Therefore, the energy of the photon must be greater than the work function in order to release the electron. The number of electrons ejected per unit time is proportional to the intensity of the electromagnetic radiation and to no other characteristic. High-intensity electromagnetic radiation consists of large numbers of photons per unit area, with all photons having the same characteristic energy, h times F. If we vary the intensity of the electromagnetic radiation and measure the energy of ejected electrons, we find that the maximum kinetic energy of ejected electrons is independent of the intensity of the electromagnetic radiation. An individual photon can give all of its energy to an electron. So the photon's energy is partly used to break the electron away from the material, or this metal plate. The remainder goes into the ejected electron's kinetic energy by the conservation of energy. This reasoning led Einstein to the photoelectric equation, where Ke equals hf minus E0, or the binding energy, where Ke is the maximum kinetic energy of the electron. Okay, so let's do a problem. So if a photon of a wavelength 525 nanometers hits a metallic cesium plate, which has a work function or binding energy of 3.43 times 10 to the negative 19 joules, what is the velocity of the photoelectron produced? So we know that the kinetic energy equals the energy of the photon minus E0, or the work function, or the binding energy. And we can relate this because the energy of the photon equals h times F. And then we can relate that to the speed of light equals lambda, or the wavelength, times the frequency. So the frequency equals c over lambda. And so we can plug that into the equation, where we get the kinetic energy equals Planck's constant times the speed of light over the wavelength. So 6.626 times 10 to the negative 34 times 3.0 times 10 to the 8 over 525 times 10 to the negative 9 meters minus 3.43 times 10 to the negative 19 joules. So the kinetic energy, or the maximum kinetic energy, is 3.56 times 10 to the negative 20 joules. And then we can solve for the velocity of the photoelectron produced by taking the square root here and then dividing this 2 times 3.56 times 10 to the negative 20 joules by the mass of an electron, 9.11 times 10 to the negative 31 kilograms. And we find that the velocity equals 2.8 times 10 to the 5th meters per second. Okay, so I want to illustrate this principle a little bit more. So I drew out a demonstration of the photoelectric effect. If we take a zinc plate after removing like the oxide layer from the outside and place it on an electroscope, we can then cause it to be negatively charged by induction. So we could take something like a PVC pipe and some cloth and rub it and touch it to the zinc plate. So we have the electroscope charged. We can then remove the charge or the electrons by shining a desk lamp on the plate. In this scenario, nothing happens because the energy isn't high enough to cause the electrons to be released, or the energy from the light or the electromagnetic radiation isn't sufficient or greater than the work function of the binding energy to cause the electron to release. So if we use UV light, then charge the electroscope, and then because the UV light is of higher energy, it'll cause the electrons to jump from the plate. So the purpose of this demonstration is to simply demonstrate that in order to release electrons from a particular material, the wave of light needs to have a high enough energy, or an energy higher than the work function or the binding energy as noted previously, in order to release that electron from the plate. So I hope you enjoyed learning a little bit more about the photoelectric effect.